In section 1.3, we're going to be taking a look at a second approach to solving or understanding a differential equation, and that's what we're going to call the qualitative approach. And as you might imagine from the name, qualitative means it's coming from the word quality. And so we're going to look at some qualities of differential equations. Specifically, we're going to kind of look at what they, how to interpret them in some different ways. So the first question up on the notes is, what's the geometric interpretation of dy dx? And if you remember back from Calc 1, probably one of the first things that you learned about the derivative was it's really about the slope. So it's the slope of the line tangent to y of x, which is, if you remember, that's the solution curve. So dy dx, when it's written as an equation, gives us a way to interpret how fast or how rapidly the solution curve is changing on the xy plane. And so this is a way of making sense of the slope in a geometric sense. But that's interchangeable with thinking about the derivative as the instantaneous rate of change of y of x. And again, that's the y of x, that's the dependent variable. With respect to t, or in this case x, the independent variable. So we can read that derivative as what's happening to the dependent variable with respect to the independent variable. Or we can think of it as kind of the slope of some tangent line to the curve. And so that means that the differential equation, if we have a differential equation, like something like this guy down here, we can read this as telling us how the solution curve behaves. Or specifically, a solution is some function y of x that gives the entire family of curves that have the same slope values at the same location. And remember, that would be on the xy plane. Right? So if you pick any point on the xy plane, whatever solves this differential equation is going to tell you what's going on at that location. This differential equation is saying, if you give me an x coordinate and a y coordinate, I'll tell you what the slope is at that point. So for example, if we wanted to see an example of this guy, we could say at the point 2, 1, the slope of any solution curve is 2 minus 1. It would just be 1. Right? Guaranteed. Right? And that's going to be the slope of the solution curve. Right? That would be dy dx equals 1. And we get that just by reading and interpreting that equation, that differential equation. Now, if I had to, I could choose a whole bunch of points, x, y, and calculate what the slope is at each one of those points. And if you imagine having a graph that shows the slope at every single one of those points, you might get something that looks like this. This is what's called a direction field. Sometimes it's called a slope field, same thing. And for us, what it's doing is it's saying at any given location on the xy plane, the little arrow is telling us what direction the solution curve must be traveling. So this allows me to do things like predict what a solution would look like. So for example, if I pick a point, like this point right here, and I say, if that point is on the solution curve, what does the solution curve have to look like? Then you say, oh, well, it would have to follow these arrows, right? It'd have to follow something like this. And we'd expect the curve to look something like that. It couldn't go from here over to here because it would have to cross through some of those, go against some of those slope field arrows. You can think about each one of those little arrows as being the little tangent line to the curve. So this allows me to see the entire differential equation, this guy, in graphical form. So what we've just done is we've created a picture of what the differential equation looks like. Now we can do this in Maple, and there's a couple of different ways. In the old days, I make a joke up here, in the old days we used to actually have to create these by hand by plotting each one of these little arrows. We'd have to plug in an x value and a y value and calculate the direction and draw the little slope arrow on there. But we don't do that anymore. We let Maple do the work for us. And so we're going to actually go into a Maple document. So let me pull that up so you can see what I'm talking about. In Maple, of course, we could desolve our equation. So if you remember, our differential equation was x of t, oh no, sorry, not x of t, y of x, there we go, comma x. And that was equal to, our equation was x minus y, so that's x minus y of x. And Maple can tell us what the solution to this looks like. If we give it a second, it says every single curve that solves this differential equation is of the form y equals x minus 1 plus some exponential, right? And sure enough, if you plug in different values for this constant, you'll wind up producing something that looks just like this, right? There's a particular solution that goes through that point and behaves like this, but Maple has solved it for us analytically. But we don't want to just view what it looks like analytically. We want to see what it looks like as a slope field. And so in order to do this, we need our DE tools library loaded and the code, and this is starting on the next page here. What we want to be able to do is figure out how to create that slope field. And so I'm just going to go ahead and name this equation here EQ, and I'm going to copy and paste because I'm lazy. I'm going to say, there we go, that equation I'm going to refer to as EQ, and Maple says, okay, I'll call that EQ from now on. And so now what I can do is I can say DE plot, not just any old plot, this is going to be a DE plot, and I'm going to DE plot the equation EQ, the variable, the dependent variable in this case is y of x, and then I need to give it a range of x values and y values. So I start by saying, okay, in the x direction, I want you to give me everything from -5 to 5. And in the y direction, notice I don't have to say y of x, I just say y. You're going to give me everything from -5 to 5. So what this is going to do is it's going to produce a slope field that views everything, all the potential curves from -5 to +5, -5 to +5. And if you look carefully, you can see there's a label for the vertical axis is y of x, the horizontal axis is x, and it knows that the vertical axis, the dependent variable, is y of x because that's what I told it right there. So this is our first direction field that we've produced, our first slope field. And so what we're going to do is pay attention to the syntax, because we're going to be able to use this same syntax again in the future. Specifically, the code for this is DE plot and then the equation, and you got to give the full equation, and then the dependent variable as a function, then the range for your independent variable, the range for your vertical axis, your dependent variable, and that's all you need in order to produce this slope field. So we're going to stop the video right here. We'll start on the next page, which kind of gets into the same thing, and we'll write down the code. But that gets us through the first page.